Have you ever heard the phrase, every end is a new beginning? Well, the stars in our cosmos seem to demonstrate this in a fascinating way. For thousands of years, humans have been witness to the result of rare and incredible events in our galaxy, the light emitted during the death and explosion of a massive star called a supernova. But it's only in the last century or so that we have come to understand that many of the well-known elements such as oxygen, phosphorus, and magnesium, elements that make up part of our bodies, were formed inside these dying stars and then spread across space in the aftermath. So how exactly do these stars go from being giant balls of energy to the stardust we're made of? Well, the precise mechanism of the explosion is still the subject of intense research. As students of science, we like to get to the bottom of things, or in this case, the core of the star where the source of the explosion is. The challenge, though, is in studying a small, powerful core that's hidden from us behind layers and layers of the star's hot, dense gas. That's what my research is about. I studied the very first second of supernova explosions, when gravitational waves are predicted to be emitted by the star's core. Now, if you imagine space to be like a massive pond, then gravitational waves would be like the ripples made by throwing in a pebble. And just like different types and sizes of pebbles produce different kinds of ripples in a pond, gravitational waves also carry unique features that tell us about their source. They stretch and squeeze space itself as they propagate outwards from the source, but crucially, they don't interact with matter like light does, and so they pass through everything unhindered and unchanged. For the supernova, gravitational waves can travel through the star and reach us in pristine condition, and their detection would give us unprecedented insight into the star's central engine driving the explosion. While detecting these ripples in space is extremely difficult, in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO for short, which uses two perpendicular 4-kilometer-long lasers to measure distortions of space, made the first direct detection of gravitational waves, those that were emitted from the collision of two black holes. This amazing feat ushered in a new era of astronomy, where we can now study the universe through a new lens. Now, as of yet, we haven't detected any gravitational waves from supernovae, but in anticipation of the first detection, my work tests and simulates how well we can see the supernova signal in LIGO detectors if one reaches us in the next few years. Because we don't know exactly what the supernova signal will look like, I use an algorithm that tries to detect the signal without making any assumptions about its specific features. By testing and tuning this algorithm on various theoretical models, I'm finding how well LIGO can distinguish between these competing models, which features of the explosion mechanism we can identify, and ultimately what we can hope to learn from the next galactic supernova.